Welcome back to this video, to the second part of the video lecture about a particle trapped in a one-dimensional box. So as we've previously left off, we have derived some of our boundary conditions right here. The fact that the wave function is equal to 0 at x equals 0 and x equals L. Okay, so how are we going to utilize this? Well, we would usually plug this in. These are our, I guess, our initial conditions into a general solution to the Schrodinger equation. Now, most of the time, or at least for me, they already gave me the general equation. General equations for the Schrodinger equation are usually rather difficult to guess or to find the correct form. So I'm just going to give it to you as well. So the general solution is this. K here is the wave number. So this wave equation, the one I've written right here, this general form is only applicable to for between 0 and L. Everywhere else, the wave function, the wave function is equal to 0. Watch the previous video if you don't understand why. But a quick reminder is just that if phi equals 0, then the probability density of our wave function will also equal 0. So you can't find a particle there at all. Okay, let's move on. So first thing we should do is plug in 0. So then we get this. So sine of 0 is just equal to 0. So and cosine of 0 is equal to 1. So we have this. We got b. Oh, forgot. This is also equal to 0 as well. So combining all of this, we have that b is equal to 0. So our wave function is much more simplified, and now we have this. This is now our current wave function. Next thing we would do is to plug in the initial condition that uses x equals L. So let me make some space. Okay. Yeah, now we're trying to plug in L. So that would look something like this. All right. This condition is I guess a bit more tricky, to say the least. All right. First things first. We gotta see what values can make this equation 0. Because there are two ways. A could equal to 0, or if KL is equal to 0, because of this identity here, the fact that sine of 0 is equal to 0. All right, so let's say that a cannot possibly equal to 0. Well, why is that? Well, if a is equal to 0, then our wave function would simply just look like this. This isn't useful because this basically says that the particle doesn't exist between 0 and L. So the probability of finding it is also equal to 0. This doesn't make any sense. Like in the last video, we've clearly established a particle can be found within 0 to L. Otherwise, there wouldn't be a particle in a box, and it would defeat the entire purpose of this quantum system. So let's just say that A can't be 0. So it leaves us with this. KL is equal to 0. Okay, so remember from trig that there's also this identity. Sine of pi is equal to 0, right? So we can also assume, therefore, you can also extrapolate it and say that generally any integer multiple of pi is also equal to 0. But for this to happen, we have to also make this, that n pi is equal to 0. Now we have two equations that we can solve, that we can put together, such that KL is equal to n pi. Therefore, we have K, the wave number, is equal to this. And we've just solved another part of our wave function. That is, phi of x is equal to a sine of n pi over L times x. Now, you might be wondering, what about the a? Well, this is where the idea of normalization comes in. So let me make some more room. Okay, for normalization, in layman's terms, you're basically trying to define the total probability of finding a particle in a given region. So let's just say this. Because we know that the particle exists in the box, that is from 0 to L, we know that if we search the entire box, we will find it no matter what. Otherwise, it does not exist. Really simple, right? So mathematically, what that looks like is this. So you take the integral from 0 to L of the probability density like so. And this is equal to 1. So this is basically what I've just said in mathematical form. We're taking the sum of all the probabilities and adding them up. Okay, and this is simply phi squared, which is this, a squared sine squared over this. So to put it all in an integral, it will look something like this. So a squared, I move the constant out from 0 to L, and we have sine squared n pi Lx. Now, I'm not going to go over the super tedious math because it's just not the main focus of quantum mechanics. But you should be able to find a trig identity online, or or your teacher might give it to you, and solving it will yield that the constant a, the constant a should equal square root of 2 over square root of 2 over L. At last, we have completed our wave function. Now, the wave function is allows you to do so. What's this? So again, what's this wave function used for? Well, if you looked at my my first video I ever made, the wave function is great at calculating the probability between two intervals in space, and calculating the probability of whether we're going to actually find the particle there or not. So like now that we have the full thing, we can technically calculate it from anything, like we can do 0 to L, we can do 0 to L over half, just half the box, or we can do a third, a fourth, a fifth. You can do anything you want, as long as it stays between 0 and L. But moreover, using phi, we can now solve the Schrödinger equation, which looks like this. Let me rewrite it, or let me write it again. If you don't know, okay. So yeah, in our situation, our potential energy is equal to 0 there. So again, ignoring the super tedious math, if you were to take the the second derivative and and plug everything in to the Schrödinger equation right here and solve for E, you would get the result this. So let me go up here. E is equal to h bar squared n pi squared over 2 times the mass of the particle that we're inspecting, and the length L squared. Okay, this is a pretty interesting result. As you can see, we have n. N is the quantum number, and it is a positive integer value. You can't have, so it's not a decimal, or it isn't like a float for you CS people out there. It's just it's a positive integer value. This is very important because this basically says that that energy of a certain value can exist. You can't have n equals 0.5. You have to have n equals 1, 2, 3, 4, 5, and so on. So this is where the idea of discreteness comes from. It comes from confinement, which is very interesting because when I first learned about it too, I didn't know where the idea of discreteness comes from. Well, in this example, it comes from the confinement of a particle within an energy barrier.